Hi everyone, my name is Joy. I'm a second year PhD student in Dr. Tuan Bodin's lab. And today I'm super excited to show you guys a couple of quick experiments that you can do with things you might have laying around the house. So let's get started. So for the first one, all you're gonna need is a bowl, a coin, and some water. So first, you're going to want to take your coin and put it inside the bowl. Somewhere you can see it slightly. And then you're going to move the bowl back until you can no longer see the coin at all. And now we're going to add water to the bowl and watch closely what happens to the coin. You can't see it right now, but look at that. The coin didn't move at all, but now you can see it. So that's pretty cool. Let's talk about why that would be. So this trick is called appearing coin, of course, since you add water and it appears. So going on to looking at the coin in the empty bowl, remember we moved the bowl back so that we can no longer see the coin. So what's happening there is when we try to draw straight rays of light from the coin to the eye, we see that it's actually blocked by the side of the bowl. And so, we can't see the coin because the bowl is in the way. But then what happens when we add water? So when we add water, the light from the coin travels in a straight line like it did before in the water. But once it reaches where water turns into air, it is bent or refracted. And because it's bent, it kind of is able to go over the side of the bowl so that you can now see the coin. But the coin hasn't moved. So where do our eyes think the coin now is? That's an interesting question. So actually, our eyes think that all light travels in straight lines, even though in reality, as you see here, it doesn't always. It can be refracted, it can be bent. But our mind doesn't know that. So it always thinks that light travels in a straight line, and it only remembers the last direction of light that it sees. So in order to find out where we actually think the coin is, we need to trace back from the last arrow that reaches the eye in a straight line like this, like the dotted lines show. Because of course our eyes only think that light travels in a straight line and it doesn't think that it bends right here. So it actually thinks that the coin is higher, like it's kind of floating in the water, which is pretty cool. So we successfully tricked your mind by adding water, bending the light, and making it think that the coin is actually higher in the bowl than it actually is, and that's why you can see it. So this concept of refraction is very cool, and it's seen a lot in nature as well. So just to recap, refraction is when light bends or changes direction when it passes from one medium or substance like air to another medium or substance like water. And so why does it change direction? Well, it's because there's a difference in the density between air and water, because water is more dense than air. And because of the difference in the density, light actually travels at different speeds. So it travels slower in denser mediums like water or maybe glass or something like that, and it travels faster in a less dense medium like air. And so when it switches between the two mediums, it changes speed and therefore changes direction. So the concept of refraction is also really cool because it explains some optical phenomenon in nature, like mirages. So a mirage, you see a picture here. It's when you see an object above or below where it actually is. So you can kind of see this in this picture. I'm not sure if you've ever noticed this on a hot day in the car, but sometimes when you look in front at the road in front of you, it will look kind of wet like this and kind of blue like it's water. So let's take a look at why that happens. So actually, it's due to the refraction of different layers of different density air. So this particular wet road phenomenon that you see happens when, usually in the summer, when the road gets really hot from the sun. So the air that's very close to the road, like these layers down here, are much warmer than the layers above it because it's not been heated up by the sun. And of course, you may know that warm air rises and cold air sinks, and that's because of the difference in density that they have. And we just learned that different density materials will refract or bend light. So in this case, light tends to bend away from warm air and towards the cold air. So let's see what happens to a ray of light that comes from the sky. So as it gets to the layers of warmer and warmer air, it bends away from the warm air upwards and to your eye. So what you're seeing, of course, is light from the sky. But where do you think that it's coming from? Like I mentioned before, our eyes only think that light travels in straight lines. So in order to see where we think the light is, we have to draw a straight line from the last arrow that reaches the eye, like this. So you can see that we actually think the light from the sky is coming from the road. And you can kind of see that in the picture, like the road, it looks kind of blue. It matches the shade of the sky. And so we're actually seeing the sky, but on the road. It's almost a reflection, but not quite. So there's actually another kind of mirage. So in the previous mirage, we saw that the sky was lower than it actually was. And in this kind of mirage, we see this ship that is much higher than it is. It looks like it's levitating. Is it magic? No, it's refraction. It's the magic of physics. So let's see how this one happens. So in this case, instead of having cold air above warm air, we have the opposite. So we have warm air above cold air. And of course, light still wants to travel, bend away from warm air and towards cold air. So if we look at the light rays coming from the ship, as it goes upwards towards the cold, warmer and warmer air, it bends away from the warmer air and towards the colder air to reach your eyes. But again, your eyes only think that light travels straight. So we have to trace back the last arrow that reaches the eye in a straight line to see where we actually think the ship is. And we see that if we trace it back, the ship will look like it's floating. So it's really a trick that your mind plays because the light is being bent by the different temperature air, but your mind doesn't know that. It just thinks that light travels straight, and you end up seeing a levitating ship, which is pretty awesome. So another phenomenon that refraction explains is why stars twinkle. So looking at the Earth's atmosphere, it has different densities because of the different temperatures and different gases in the atmosphere. And they're not perfect layers, but they still are able to refract light. And so if you think of light from a star coming into the Earth's atmosphere, it's refracted this way and that until it reaches your eye. But the catch is that the atmosphere is constantly shifting and moving. And so the path that the light takes from a star from 1 second to the next is slightly different. So because the atmosphere is changing constantly. And so 1 second, it will take this path and you see the light maybe slightly shifted to one direction. And then the next second, the atmosphere changes, the light takes a slightly different path, and you see the light maybe slightly shifted again. And the light that was there before stops, and that's the twinkle that you see. So the same concept of refraction explains why the coin reappears in the bowl, why stars twinkle, and why mirages happen, why you can see floating ships. So let's move on now to the next experiment. So for the next experiment, you're going to need a glass cup, or you could use a 2-liter bottle, anything that's clear and has relatively straight walls that will hold water. Some paper or cardstock, a marker, and some water, of course. So what we want to do is draw 2 arrows, or just 1 arrow, on this sheet of paper and place it behind the glass. I have it all set up here. And note which direction the arrows are pointing. They're both pointing that way. So now I'm going to slowly add water to the glass. Look at that. The arrows switch directions. So now they're pointing in opposite directions. And if we fill it all the way up, they will both switch. Look at that. Okay, so here are the 2 cases. On the top, you have the empty cup with the arrow pointing to the side. It looks like it's pointing to up because we are looking at the experiment from the top, but it's pointing to the side. And then the bottom case is when the cup is filled with water. So in order to illustrate what the light is doing here, we're gonna track the path of the light from the very top of the arrow and also the path of the light from the very bottom of the arrow here. So we're looking at the light, how the light travels from either end of the arrow. So then if or when the arrow flips, we'll be able to see that in the light paths. So let's look first at the cup that's empty. So Here I've drawn two arrows representing the light that's from the top tip of the arrow and from the butt of the arrow. And of course, the light travels straight until it's hit something like we've established before. So once it hits the cup, because it's empty, you're going from air to air. You're not going from air to water. And because the mediums are the same, the light basically travels straight through the cup and towards your eyes. So your eye sees the same arrow pointing in the same direction. But what about the case where the cup is full of water? So again, the light from the tip and the butt of the arrow travels straight until it hits the glass. And now we are going from air to water. And so there's going to be a larger refraction, and the light's going to be bent. So that's what we see. And the direction the light's bending in depends on the two mediums. So in this case, it's going from air to water. That affects how it's bending. And also the curvature of the glass and the angle at which the light hits the glass also changes the way that the light is bent and refracted. So now the light the refracted light travels through the water in a straight line, but at the refracted angle, until it hits the other end of the glass. So because this is another transition from two different media, so from water to air this time, the light will be refracted again. And when it refracts, you can see that the two rays actually cross each other. So the light from the tip of the arrow ends up where the butt of the arrow was, and the light from the butt of the arrow ends up where the tip of the arrow was. So that means that what you see is the arrow flipped. So actually, this is something you can add on to the experiment at home. If you look at the arrow very close to the glass before the rays have crossed over, the arrows will point in the same direction that it did when the cup was empty. So this point where the two light rays cross is called the focal point. So if you are behind the focal point, you will see the arrow upside down. But if you are in front of the focal point, you'll still see the arrow right side up. So feel free to try that at home. So moving on to our next demo, we're gonna make a light fountain. This one I think is really fun. So all you're gonna need is an empty 2-liter bottle, soda bottles, or any other plastic large bottle would work. You'll need something sharp like a nail, or in this case, I have a small screwdriver, something that will be able to poke a small hole into this. And then lastly, you'll need some water and a flashlight. I'm going to use my phone again, or a laser pointer if you have. So first, you're going to take your sharp object and poke a small hole towards the bottom of the bottle. And I chose this spot. You want to try to make the hole round and kind of small so that you get a nice regular stream once we fill this up with water. All right, so for our next steps, I'm gonna head to the sink because it might get a little messy. All right, so So the next step to do by a sink is to fill up the 2 liter with water. And of course, once the water level gets above the hole, it's going to leak out through this hole. And you can block it with your finger, or you can just let it be. I'm going to block it. Okay, so once it's pretty full, you can cap the bottle. Once you cap the bottle, the water should not really leak out from the hole. Okay, so what we're gonna do is loosen the bottle cap. Once I loosen the bottle cap, the water will stream out from the hole that we made, and I'm going to shine my flashlight into the water and see if the light can go into the stream. So let's unscrew the bottle cap. And you see the stream there immediately. You can control the flow of the stream by loosening and tightening the bottle cap. And then we're going to take our flashlight and shine it behind. And watch the stream. We turn off the light. Isn't that cool? I can still open and close the bottle cap. The light seems to be trapped in the water. And we can also try the laser pointer. So you want to aim the laser pointer from behind at the opening of where the water comes out. There you go. You can see that the laser light follows the water stream.
Hey, it's me from the future. I'm here to remind you to be safe and to make sure to have an adult with you for this experiment. If you're using a laser pointer, remember it is not a toy. Do not point the laser pointer at anyone. Do not point it at a mirror-like surface or a mirror, as it could reflect the laser somewhere dangerous. Okay, that's all. Back to past me for the explanation.
So looking at this model of what we just made of the light fountain. So we shine a laser pointer at the stream from the opposite end of the water bottle. And the laser beam travels straight until it reaches the water to air interface, so the boundary between 2 different density mediums. And from what we learned before, we would expect the light to refract, to bend. But actually, this is a really special case. And instead of just, bending into the air, it reflects. So this is called total internal reflection. And the result is that the light actually stays inside the water stream. So it's reflected, then it hits another boundary, and it is reflected again, and this just keeps happening. And this is how the light is trapped within this stream of water. It just keeps being totally internally reflected. So total internal reflection happens in a very special case. So total internal reflection happens only when you meet certain requirements. Total internal reflection happens only when you meet certain requirements. So the first one is that the light has to be traveling from a denser medium to a less dense medium. For example, from water to air, like the light fountain. And also, the angle at which the light hits the boundary has to be big enough. And so if those two conditions are met, then the light will be totally internally reflected. And this is a super interesting and useful principle because you're able to basically trap light in a stream of water or in a thin tube. And that's really useful for transmitting information. And we really want to use light to transmit information because it's so fast. You know, it's the fastest thing in the universe. So if we can use that to transmit information, it will be much faster than, say, electrons that we use now. So that's what fiber optic internet is. So you may have heard about fiber optics. There's a big transition now from cable internet to fiber optic internet. And what has really allowed fiber optic internet to work is total internal reflection. So these wires, they kind of look like regular, or these fibers kind of look like regular wires. But instead of having a copper core, like regular wires that conduct electrons, they have usually a silica or glass core. And that glass core conducts light. So if you look at this diagram of a example of a fiber optic, it has this structure where the core is usually silica, and there is something surrounding it called the cladding. So this cladding has a density or a refractive index that makes sure that total internal reflection will happen to keep the light trapped inside this core. And you see that once the light enters the core, it's totally internally reflected so that it's contained in the core and also transmits in the direction of the fiber. So fiber optic internet uses light to transmit these signals instead of electricity or electrons. So let's look at how they compare. Is fiber optic really that much better? So optical fibers, again, conduct light, whereas copper wires for regular cable internet conducts electrons. And fiber optics are able to transmit signal at 69% the speed of light, whereas cable internet transmits signal at less than 1% the speed of light. So that's more than 69 times faster than cable internet. And on top of that, fiber optic internet is actually also more reliable and more secure. It's less susceptible to different natural events that might disrupt cable internet and cause power outages. And also it's more secure because it doesn't use electricity, where electricity can't be contained just within the wire. It still transmits some signal that can be detected outside. Whereas the light in an optical fiber is completely contained inside the fiber and no light can escape. So there's no way that you can measure a fiber optic signal outside of the fiber itself. So it's more reliable and more secure. So for our last demo today, we're going to make a sky in a glass. So what you're going to need is a glass of water, or in this case, I have a big pitcher of water. You're going to need a little bit of milk. These are going to act like the gas particles in the atmosphere in the sky.
Gonna need something to mix it with and a flashlight to act like the sun. I'm gonna use my phone again. So first thing to do is to add a bit of milk into the water and stir it up. So here the particles of milk floating in the water act like the gas particles that are in the atmosphere. And next we're gonna turn on the flashlight and shine it on the side. Can you see that the milk water mixture looks kind of blue? So what's happening is that the milk particles are scattering the blue light much more than the other colors of light. And this is also what happens in the sky. The gas molecules in the atmosphere scatter the blue light 10 times more than the other colors of light, like red. And so the result is that when we're looking at the sky normally, it looks blue because more of the blue light is scattered and in the sky. But when you're looking at a sunset, it doesn't look blue. It looks yellow or red. And so to simulate that, we can shine the flashlight behind and look directly at the light. It's a bit harder to see on camera, but you should see that the light looks yellow, kind of like the sun at sunset. So I hope you can try this at home so you can really see the big difference with your own eyes. But what's happening here is that this ray of light that's from the flashlight, as it's traveling through this milk and water, the blue light is being scattered or bounced off in all different directions. And so by the time it's traveled all the way through this mixture, most of the blue light has been scattered away. So what's left is the red and yellow light, and that's what you see. That's also why during sunset, you see a red sun, because the light from the sun has passed through the atmosphere for a long distance. So all of the blue light, or most of the blue light, has been scattered away, and what you're left with is just the red sun. So you can also try shining your flashlight beneath the glass, and you can see that from the side view, it looks blue again. But if you look from the top, again, you can see the red sunset kind of look. So let's just talk a little bit more about how that happens. So let's talk more about what's happening in the sky in a glass. So we have the glass of water, which we add milk to, and then we shine the flashlight. And when it hits these milk particles, scattering happens. And like I said previously, the scattering is dependent on the color or the wavelength of the light. So it scatters blue the most. So there it goes, scatters the blue light, which goes every which direction in the solution and makes the solution look a bit blue. And then, since the blue light has been scattered by some of the milk, the light ray from the flashlight becomes more and more yellow or red. So it can, the light ray can hit another milk particle, scatter more blue light,
and become yellow or red. So if you're looking directly into the flashlight, like the eye is showing here, what you see again is the sunset-like yellow light coming from the flashlight. And that, again, is because you're looking directly at the light ray that has had its blue light scattered by the milk water solution. So what's left is the yellow and red light, which travel to your eye. So this is like what happens in a sunset. But if you remember the case where we're watching from the side, so you're not directly looking at the flashlight ray of light coming from the flashlight, you see that the solution, the milk and water, looks kind of blue. And so what you're seeing there is all the scattered blue light from the flashlight. But because the flashlight's ray isn't going directly into your eye, you're not really seeing the beam from the flashlight, but you are seeing all of the scattered blue light. And so that's like looking at the sky, not during sunset. So again, this is why the sky is blue. So when the sun hits the atmosphere, right here, it's white light, so it has all the colors in it, but the gases and small particles in the atmosphere scatter the shorter wavelengths, the blue light and the purple light, much more than the yellow and red light. So that's what this is showing here. And so there's a lot of blue light that's been scattered in the atmosphere to make the sky look blue. But what happens during sunset? Because, beautiful sunsets are all different colors, red and pink and yellow. So it really has to do with the path the sunlight has to take to get to your eyes. So on the left here, you see an example where you're looking at the sky, but it's like afternoon or noontime. And you see that the sun is directly above you. And so the distance it has to travel in the atmosphere to reach your eyes is relatively short. And so there's not enough time, or there's not enough distance for the blue light to be scattered so much that the sun looks red. But it is scattered a little, because when you look at the sun in the afternoon, please don't look directly at the sun. It's dangerous. But we all know that the sun looks kind of yellow. That's because some of the blue light is being scattered. But if you look at the sunset case, the sun is no longer directly above you. It's to the west, by the horizon. And because of that, you can see that the light has to travel a much longer distance through the atmosphere to reach your eyes. And so that gives more distance, more time for the blue light to all be scattered away into the atmosphere. And so the light that reaches your eyes becomes red or pink or whatever color it happens to be. So it's pretty cool that we can simulate the particles in the atmosphere just by mixing milk and water. Okay, so that wraps up my last experiment, but let's talk about what we learned today. So from the first two experiments, the appearing coin and the switching arrow, we learned about refraction, which is when light bends when it travels from one medium to another, like from air to water or from water to air. And again, that's because the light travels at different speeds in mediums of different density. And we also saw that
refraction is what makes stars twinkle and what makes mirages happen. And we also learned about total internal reflection with the light fountain. So again, in special cases, the light, when it hits a boundary between two mediums like air and water, in certain special cases, instead of refracting, the light will be completely reflected. And this is the principle behind fiber optic internet. So you can keep light trapped basically within a optical fiber and transmit information basically at the speed of light through this fiber using total internal reflection to trap the light. And lastly, we just talked about scattering and why scattering makes the sky blue and the sunsets red. So by scattering the blue light more than the yellow and red light in the atmosphere, we see the sky as blue normally, but during sunsets, when the sunlight has to travel through more of the atmosphere, most of the blue gets scattered away and we see a red, beautiful sunset. So I hope that you guys had fun learning and listening to me. And I hope you guys get to try out some of these experiments on your own and see what you can observe.